Hello and welcome to episode 4 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode we are going to finish our discussion of threads by taking up the sample problem we introduced at the end of last class, and then we're going to start a new topic, which is the consequences of multi-threaded programs, and discuss things like synchronization. But first, the operating system of the day. So today's operating system is one which you might have heard of, maybe. It's called MCP, Master Control Program, and this was released in 1961 from the Burroughs Corporation. And this particular operating system ran on a variety of Burroughs machines, including the small, medium, and large, and has actually been around for quite a long period of time. And it's gone through many name changes, coming from Burroughs, going to Unisys ClearPath, and so on and so forth. And if you're really curious about this operating system, if memory serves me, there's actually an in-browser simulator for it, which is kind of cool. Now, why is MCP important to know about? Well, it's the first commercial operating system to do a number of really, really important things for modern OSs. So, for example, MCP was the first operating system to be written entirely in a high-level language. So if you look at previous operating systems, they were for the most part implemented in assembly languages instead of something like C. You can imagine that probably wasn't that fun to do. Now, while I personally like doing assembly programming, most people don't. Now, other things that MCP offered were support for multiple processors, which was a fairly new concept. They had multitasking and threading, at least at the hardware level of support in 61. And they also were the first commercial operating system to implement virtual memory, which we will be talking about in a few weeks. Now, aside from that, as we look at what are some of the other features that MCP really brought to the table, you're looking at things like journaled file systems, high-level job controls, the concept of ports, although there are many meanings to that particular word. But one of the really neat things about MCP is that they figured that if you're going to be purchasing one of their big machines, which was the only thing that MCP actually ran on, then there was no reason to charge you extra for the operating system. So we're going to give you the source code to the operating system. Now, why was this cool? Well, this is cool because any of the people who had a Burroughs machine had the source code to the OS, and if they found a bug, they would fix it, and then they would share the bug fixes with each other. So in a way, MCP is kind of the beginning of this kind of open source movement where you have users contributing patches and new utilities and new programs. So that's kind of cool. And MCP actually spawned, or spawning is not the right word. MCP is kind of like the great grandfather of many other operating systems, or at least operating systems ideas. Now, I mentioned that MCP was written in a high-level language, and you might be wondering, oh, so it was written in C. No, it wasn't written in C. It was written in a Burroughs variation of a language called Algol, and they've called this language SBOL. And when I was searching the internet, I actually managed to find this cool thing. Let's see if I can get it up here. No, I don't want that. So I found this really cool manual for Burroughs SBOL, and this actually goes through what the spec of the Burroughs SBOL language is. So we've got things like grammar specifications in here. So this is kind of a fun thing, and I'll post it to Piazza in case you're curious. Obviously, this is not useful, but it's just kind of neat to see. And if you're interested in seeing what does a language grammar actually look like, or a language spec, it's also really cool to see that. So I'll post this lovely little manual to Piazza. It's pretty cool. And yes, it's kind of hard to read from the perspective of this was not printed on any kind of modern typeset system, but it's still a cool read. All right. So, what happened in our last episode? In our last episode, we were discussing threads. And in fact, we discussed how preemption and threads actually works. Because if you're looking at any modern system that implements concurrency, you're not just looking at having basic hardware support, you're also looking at actually having to share the limited number of CPUs between a vast number of threads. And so to do that, we use preemptive time sharing. And the idea behind preemptive time sharing, of course, is that we're going to rapidly switch between all of the threads that are ready to run. And how we're going to implement that in particular is by setting a time limit that says, give the current thread such and such time to run, and if it hasn't yielded, terminated, or blocked before that timer expires, then we're going to involuntarily kick it off the CPU and give another thread a chance to run. Now, we implemented this preemption using a hardware device, and that device we used was the clock. And there's various ways that you can implement preemption with a clock. We're not going to worry too much about that right now. Now, how long do you set the scheduling quantum for? That is the maximum amount of time a thread is permitted to run on a CPU for. That really depends on the systems that you're expecting your operating system to run on. That depends on what level of real-time behavior do you wish to offer to your customers. And it also just depends on, how do you implement the OS and so on and so forth. Some operating systems, such as Solaris, have offered anything from a 200 millisecond scheduling quantum to a 40 millisecond scheduling quantum. And I'll explain exactly why they had a variable scheduling quantum when we talk about scheduling closer to the end of the course. Now, not every operating system, by the way, has a different scheduling quantum on a per thread basis. Linux, for example, has the same scheduling quantum for every thread. But operating systems like Mac OS, Solaris, and Windows actually have different length scheduling quantums. Again, we'll talk more about how that works later. All right, so before we go on to taking up the sample problem, what I would like to do is just review one other brief thing with you, and that is the different reasons that we get context switches. So I'm going to switch here. Let's go to that one. And open up the threads here. So I want to bring up a diagram here just to refresh you. It's really important to keep this in mind. There it is. All right. So what I want to remind you of is there are three primary states that we look at when we're talking about threads. They're the ready threads, the running threads, and the blocked threads. Ready threads, remember, are threads that are not currently running but could run and actually execute instructions should you select them. Blocked threads are waiting for something, and we're going to talk more about what a blocked thread means over the next few lectures. And then a running thread is any thread that's actively executing instructions on the CPU right now. And there may be only one of them if you only have one CPU with one core, or there may be more depending on what kind of system you have. Context switches happen when you go from running to ready or running to blocked, or running to exit. So you're going to have a context switch under 4 different circumstances, actually. So there's thread yield, which is you voluntarily give up the CPU. There's being preempted, which is involuntarily giving up the CPU because you ran out of the scheduling quantum. There's terminated, because of course, if a thread terminates, you're going to want to run another thread right behind it. And then the fourth one is the current thread that was running needs to wait for some resource, and so we need to put it to sleep, and we're going to have a context switch there. And we're going to talk more about the sleep operation later today. But before we get into our new topic of synchronization, let's actually go back to the sample problem from last day. Now, if you're sitting there at home right now, the sample problem from yesterday, Tuesday that was this one called 2 threads. And there's 2 parts. So the first thing we need to note is that both threads are going to run the same block of code which is going to do C milliseconds of compute and S milliseconds of sleep. And it's going to repeat this n times. And then the thing I mentioned you should pay attention to is how does the length of the compute time compare to the length of the sleep and compute compared to the scheduling quantum. Now for part A, you'll notice that compute time is less than sleep and compute time is less than the scheduling quantum. So what's interesting about this particular thing is that preemption's not going to happen here because the compute time, which is the time we're actively executing instructions on the CPU, is shorter than the scheduling quantum. So we're actually going to context switch before the quantum expires, and so we'll never actually be preempted. So I'm going to switch over to OneNote here, and we will take a look at how to do this problem. All right. Sorry, I'm just waiting for my tablet to wake up. Wake up, tablet. All right. Well, that doesn't want to work. So let's just type this out. Let's make R. Oh, maybe? No. So what we're going to do here, and that text is a bit too small, so let's switch over here to just VI for a moment. Maybe my tablet will pick up eventually. All right. So in part A, we've got our compute is less than sleep and compute is less than quantum. So I'm going to use our sleep time to be 4 S's. Let's not use S's. We're going to say sleep time is 4 Y's, and I'm going to use our compute time to be, let's say 3 X's. Now, it's not specifically saying, oh, well, compute is 3 and sleep is 4. I'm just using X's and Y's for the purposes of making, there we go. Of course it comes up now. I'm just using X's and Y's to indicate this block is shorter than the other. I'm going to go back over here because I like writing more than I like typing. All right, so we're going to want to actually dry. Okay. There we go. So thread 0 always goes first. And anytime you see a problem like this, always assume thread 0 goes first. And so thread 0 is going to do its compute. There's its compute. And then immediately after doing its compute, it goes to sleep. And I'm going to try to draw very neatly. All right. Now, when does thread 1 actually get a chance to run? Well, the second that thread 0 context switches from running to sleeping, thread 1 gets a chance to do its compute cycle. And what's interesting here is that it's going to fall asleep while thread 0 is still asleep. Now, a common mistake that people think here is that when thread 1 goes to sleep, thread 0 can wake up. But that's the thing about sleeping. If somebody says you need to sleep for S milliseconds, then you will sleep for the entire S milliseconds, regardless of whether or not there are other threads running on the CPU. So these two threads are going to be sleeping at the same time. All right. Now, I'm going to draw this little dotted line here. Once thread 0 has completed its sleep, it will wake up. And since thread 1 is asleep, it can do its compute. And then it falls asleep. again. And if we keep drawing this out, what you'll see after some number of cycles is after the final sleep for the first thread, that's what we get. Now, the question is, how long does it take for both of these threads to finish? Okay. Well, what we notice here is that this particular repeating block, let's change colors. This is a repeating block. And this happens, this is C plus S. So that's the time it takes to do a complete cycle. Now, you'll notice that in each of these repeating blocks, thread 0 does its whole compute followed by its whole sleep, and it never has any extra sleep time. So since each thread is going to execute that n times, you're going to end up with n trying to erase here. Never works when you want it to. N C plus S. Now, have we got the final answer here? And the answer is no, we don't have the final answer yet. What we've missed is we've forgotten this little bit here. Now, you might be thinking that little bit doesn't matter because it's a sleep. Do we really need to count the sleep time when we are computing the total runtime? And yes, you do, because thread 1 isn't going to finish until it's finished its final sleep. Now, what's the length of that? Well, the length of that is actually C. Now, why is it C? Well, the reason why it's C is because if you actually look at this, what's the offset, the length of time here? The difference between when thread 0 starts and thread 1. And the length of that is C. And so the pattern is shifted over by C for thread 1. So the answer for part A is N times C plus S plus C. All right, now what about part 2? That was weird behavior. Try to get a new window here. Oh, this thing is being annoying. All right, part 2. So let's go down and look at part 2. So for part 2, I'm going to do it in blue here. Here's what we've got. Maybe you don't remember the problem. Part 2. So now, instead of having the compute time less than the sleep time, now we're actually going to have the sleep time is less than the compute time, and the compute time is still less than the scheduling quantum. All right, so let's go back to OneNote then, and let's take a look at that one. You know, it's really funny. OneNote's behaving very strangely. I tell you why this is funny. It's funny because it actually updated last night. It said, oh, bug fixes, bug fixes. Yeah, it doesn't look like they did any bug fixes. Looks like they broke it. All right, so we have S is less than C and C is less than Q. So this is part B. So for part B, we've got S less than C, so let's let S be 3Ys and C be, well, let's let it be 4X's this time. Kind of the reverse of the situation we had before. And as always, thread 0 is going to go first. So there's thread 0, and there we have thread 1. All right, so compute, 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 sleep, sleep, sleep. Now, while thread 0 is sleeping, thread 1 finally gets to run. This is where things get interesting. What happens when thread 0 is done its sleep time, but thread 1 isn't done its compute time, and the scheduling quantum hasn't happened? Should there be a context switch? There's not going to be a context switch. What's going to happen is, since the scheduling quantum hasn't expired, thread 1 can continue running on the CPU. And thread 0 is going to be moved to the ready pool, and it's going to have to wait its turn to be selected. So we're going to represent an extra sleep by the letter Z. All right. Now thread 1 is going to do its sleep cycle. And at this point, now thread 0 can actually go again. And since the sleep cycle is shorter than the compute cycle, we're going to have the threads doing a little bit of an extra sleep while they wait their turn for the other thread to give up the CPU. And this pattern continues. Like so. All right, now the question becomes, what's the runtime of this? How long does it take for both the threads to finish? So let's again look for repeating blocks. Now, here's an interesting observation. One of the ways that you could look at this is that these two threads take turns doing their compute cycle. So we've got 4 compute, 4 compute, 4 compute, 4 compute. So there is actually a repeating block. And the length of this block is C. So then the question becomes, if the length of that is C, how many of these blocks are there? Well, since the threads are taking turns and each thread is going to do n blocks of C, we actually end up with 2nC. But we're not quite done yet because we haven't considered this right here. So now we just tack that on to the end. And so for part B, you should get 2nC plus S. All right. With that then, I'd like to end our discussion on basic threading. And now I would actually like to move on to our new topic. So here's some basic observations that we have about threads. We have a bunch of threads in the same program. And if you remember, we discussed that all of those threads have shared access to the code segment and to the data segment. That means that all threads share the code. All threads also share the global variables as well as the heap. The only thing they don't share is their stacks. Now, that does some very good things for us. By having threads have shared, of the same program that is, have shared access to things like the global variables in the heap, that gives the ability for the threads to actually communicate with each other. However, there's consequences. What happens if you have some global variable that is counting how many students are in the room right now? And I know, since we're not actually on campus, the number of students in the room right now is 0, or yourself, which is just you in your room, maybe in a cat or something. So what happens if we have this counter anyways, and it's a global variable, and what happens if 2 students enter the room at the same time? We would want to increment that counter twice at the same time. What happens? Or what happens if one person leaves the room and one person enters the room at the same time? What I'm trying to say here is, what if multiple threads are trying to read and write the shared variable at the same time? Is there going to be any consequences to this? Or is this okay? Well, this is normally where I would show you a very silly video, but I've decided the silly video is a little too silly and also needs to be updated. So instead, what I'd like to do is let's write a piece of code and see what happens when you have threads reading and writing a shared variable at the same time. So I'm going to open up our code here. Here it is. It's nothing complicated. So I have a shared variable here called total, and n is the number of iterations that's going to happen, and n has been set to 1 million. Then I have this function add, and add is going to add 1 to total 1 million times. Subtract, on the other hand, is going to subtract 1 from total 1 million times. Very simple code here. Now, I've decided in this case, I know last class I showed you pthreads example, so today I'm showing you another example of using OpenMP. So here I am creating 2 threads with OpenMP. So I have pragma OMP parallel num threads 2, and then if I'm going to have the first thread, the one that's numbered 0, run the add function. That's going to be its entry point. And then the entry point, the code for the second thread, is going to be subtract. And then I'm going to print the total. And the question is, what's total going to be? Now, if I have one thread add 1 a million times, and I have a second thread subtract 1 a million times, the answer should kind of be obvious. The answer should be total should have 0 at the end of the day. You effectively did a whole bunch of work for absolutely nothing. And that's what we want the result to be. We want the result of running this program to be 0 in total. The question is, will it actually be 0? So let's open up the terminal here, and let's actually run it. Oh. Well, that says I have negative 185,421. I don't know about you, but that's not what I wanted in my bank account. Maybe we should run this program again. Oh, I like that balance. 231,000? We can do that. Let's do it again. Ooh, even better. 551,000. Better run this again. You know, I'm on a roll. Let's see if I can get even better. Oh, I busted. Well, this is interesting. Each time I run this program, I get a completely different result. What's going on here? What are all of the possible outputs? Well, first off, what's going on here is that we have no control over which order threads actually run in. And as we're going to see, when you have multiple threads reading and writing to a shared variable, order of thread execution matters. And we'll look at this in greater detail in a few minutes. So because we have no control over the way the threads actually execute, it means that each time I run the program, it's almost as if it's running something completely different. That's not what I like. Now, what are all of the possible outcomes of this particular program? Well, I'll tell you the answer now, and when I show you the assembly as to what's going on to cause this specifically, hopefully you'll understand how I arrived at this answer. So the total number of different outputs this program could have is between -n and +n. So you're looking at like 2n plus 1 different outcomes for the same program. All right. Obviously, this is not what we want to happen. So, what is going on? So now, if you're following along at home, we're using the synchronization slides, which are posted to Piazza, of course. Or not Piazza, they're on the course website. So, we've already talked about all threads having shared access to global variables and the heap. So here is actually the same bit of code that I just demoed for you, except now we're going to use OS161's library instead of OpenMP. So we've got a shared global variable, and now you see this underscored word volatile. We're going to ignore that today and probably next class, and we're going to come back and talk about this later. We've got an add function that's going to add 1n times and a subtract function that's going to subtract 1n times. And we know from our little demo here that this code as it stands, even though if n is some specific value like 1,000,000 and we want the answer to be 0 and we know the answer should be 0, we have seen that this code doesn't produce 0 necessarily. Why? Well, here's the problem. What we have is what's known as a critical section. This block of code right here and this block of code right here are critical sections. These are a region of your code where it's very important that we control thread execution. Why do we need to control thread execution through a critical section? Well, when we see total plus plus, we see a single line of C code, and so we're not thinking about what that actually means in assembly. We see total plus plus, we see one line of code. We see an operation that can't be interrupted, but that's a lie. Total plus plus, if we convert that to assembly, is at minimum 3 or 4 assembly instructions. The first thing we have to do is we have to load the value of total, and remember total is a value stored in memory. We have to load that value into a register. We can't in MIPS add and subtract directly from an address in memory. So we have to load the value of total into a register. In this case, we've loaded total into register 8. And then what we're going to have to do after that is we have to load this was loading the address of total into register 8. Now we have to load the value of total into register 9. Then we add 1 to it, and then we have to update the value of total in memory. So that total plus plus single line of code wasn't one line of assembly. It's 3 or 4 lines of assembly. Context switches can happen anywhere. A context switch can happen here, it can happen here, it can happen here, and it can happen here. And you have no control whatsoever over when those context switches occur. You don't know when the clock is going to throw an interrupt. You don't know when your network card is going to receive some data and it's going to cause a context switch for some reason. You have no control here. And because of that, that means that we can have context switches happening before we've had an opportunity to store the updated value of total back to RAM, which means the other thread that starts running would have the incorrect value of total. And the same, of course, is true for subtract. So let's actually look at a few executions here to see what's going on. So this first example is the optimal, the way we want it to be. So what we want to happen is we load the address of total, we load the value of total, we add 1 to our register's record of what total is, and then we're going to update total in memory again. Then we get the interrupt, which causes the context switch to subtract. It goes through all of its instructions, and at the end of executing this whole slide, we end up with total is 0, which is exactly what we want and is exactly what is expected. But you have no control over this. This is just as likely to happen. So what we could have happen is the add thread loads the value of total into register 9, updates register 9 by adding 1 to it, and then before we get an opportunity to save total, we context switch over to thread 2, which is going to perform the subtraction. Now it doesn't know that you have, because it is a separate thread, and the computer doesn't really know that there are separate threads. So it's going to load total into register 10. Now total, it thinks, was 0, even though we had already updated it, just forgot to do it in memory yet. So it subtracts 1 from 0, and then it gets to write to memory that total is -1. And now that it's done, there's a context switch back to thread 0. And now, we continue from where thread 0 was executing, and we're going to save our value of total, which was 1, to total. So now, at the end of executing these two threads, total has value 1. And in fact, what's interesting is it's as if thread 2 never even ran. All of this work that thread 2 did got thrown away. That's absolutely ridiculous. Okay. So now what? Well, here you go. Maybe you're thinking, well, what if I just, instead of doing preemption, what if I let the two threads run at the same time by having 2 CPUs or 2 cores? Do we end up with this particular problem still? And the answer is yes, of course you do. So the 2 threads are running on separate cores. So they both load their values of total at the same time. So thread 1 is going to have R9, total of 0, and thread 11 has the value of total, which is 0. So both threads running on separate CPUs at the same time are going to have value 0. Thread 1 is going to increment register 9 to 1. Thread 2 is going to decrement it to 11 or to -1. And then they have to both store their value. Now you'll notice here the stores don't happen at the same time. And that's because the memory controller can't perform 2 writes at the same time. So they won't go in parallel. But in this case, we're saying thread 1 got its save in before thread 2 did. In which case, the final value in total is -1. And it's as if thread 1 never ran. So we have a problem here as well. Now we have a question here on Piazza. What happens if you do not use volatile with total? Possibly very bad things. So for any shared variable that you have where multiple threads could be reading and writing, you should be making it volatile. We'll talk more about volatile another day, but very briefly, volatile is disabling a compiler optimization that can cause a race condition, which is the particular name of the problem we're dealing with right now. But we'll go into greater detail about what volatile does later. All right. Now, there's a name for what's going on here. So each time I ran this program here, we got a completely different output. When you have a program whose output or result completely depends on the order of thread execution, we say that that program has a race condition. And a race condition is usually a bad thing. My understanding is that Google has this new software analysis tool, and they ran it on the Linux kernel, and they found something like 300 race conditions, deadlock situations, and live lock situations. That's pretty impressive. And yet Linux still works for the most part. Race conditions, however, for the most part are bad. Now, the race condition that we had in this particular example was a race condition where the output of the final program was different depending on the order of thread execution. Race conditions don't always present themselves in such a friendly way. Sometimes race conditions present themselves in much, much uglier ways. So, race conditions. This is, again, where the order of execution of the threads creates the output of the program. There are 3 sources of these race conditions we're going to talk about. Today we're only going to talk about one, and that is your fault. It's you who misimplemented your code to not take these race conditions into consideration. Usually it means you haven't protected a critical section. And a critical section is an area of your code where you have multiple threads possibly reading and writing the same shared variable at the same time. The other 2 sources of race conditions we'll talk about another day. And they're not your fault. Let's look at this other piece of code here. Now, this particular piece of code is something a bit more useful. This is a shared list. And what you've got here is we want to be able to remove the front of a linked list. And we're going to have some assertions about you can't remove the front of an empty linked list, and we'll actually return the value. So is there a race condition in this particular piece of code if multiple threads were going to run this at the same time? So let's actually think about this here. So what I'm going to do is let's go over to OneNote again. And let's go home, insert pages. Let's do a new page. There we go. Let's draw. Let's do a black pen. So kind of make these 2 things show up on the screen at the same time. What we're going to do is, let's suppose that we have a list that contains a single element. And that single element is going to be the value 87, and first is going to point to that, and we also have a last pointer, and it's going to point to that. All right, and then of course the next pointer for this particular element is null. All right, so there's the list that we have. Now thread 0 and thread 1 are both going to call remove front at the same time. All right, so we're going to get element. We've asserted, so we do our assertion, which is true. The list is not empty while thread is running. And then we're going to set element is equal to LP first. Great, right? Okay, let's do a context switch. Okay, now thread 1 gets to execute. And let's assume that thread 1 is going to execute remove front in its entirety. So we assert non-empty. We're going to set our element pointer to point up to here to the first, all of these things. And the consequences of this running is that we're going to end up erasing this. And now first and last are going to both point to null. And you can see here that's actually this special case right here. Since first is equal to last, when thread 1 notices that it's a single element list, we set first equal to last equals to null. Great. we decrement the counter of the number of things in the list. So now the count is equal to 0, and we free element, and we're going to return number. All right, so our list is now empty. The front has been removed, and now we have a context switch. And now I'll draw some arrows here, make this a little more obvious. And now the thread 0 is going to run. Now thread 0 has a pointer to what it believes was the first of the list. And now it's going to execute this line here. Num equals LP first item. And guess what happens? We end up with getting a memory error. And the reason why we get a memory error here is because we are trying to dereference freed memory, and we simply can't do that. Now this is just, by the way, one possible way that the race condition could show itself in this particular piece of code. So this code here, the critical section, is pretty much the entire body of this function. And this race condition here presented itself in our example not as an incorrect final output, but as a segmentation fault, a runtime programming error. There's a question about not being able to attend the lectures live. When will we be able to start the first assignment and have covered enough content to start it? So you should have already, A0 you don't need any content for, and you should be able to do assignment 1 in its entirety, hopefully by the end of Tuesday's class next week, but you're always welcome, of course, to read ahead. And you'll have enough for the first part, hopefully today. We'll see how much time we've got here. At the very least, you'll have it tomorrow, Tuesday. All right. So this is the example of the segmentation fault for a race condition from this code. Let's look at another list function here. So this is the list append function. Now we want to know, is there a race condition if we have two threads trying to append at the same time? So let's get a new page here. And let's take a look. So we've got a list again. And in this example, instead of having a list that contains one element, I want to have a list that's empty. So first and last are both going to point to null, and my count of elements in my list is going to be, of course, 0. All right, now let's do our two threads again, just like we did before. Thread 0 is going to start. So thread 0 is going to malloc an element. All right, so we're not connecting it up to anything yet. So I've malloced some space, and this is element. And then I'm going to set the value of the element. Let's set it to 87 again. And I'm going to assert that it's not in the list, which it isn't because the list was empty. We're saying we can't have a list of duplicates. And then we're going to check, is LP empty? Yes. So we're right here, and we're just about to execute the body of that branch when we get our good friend context switch. And now thread 1 is going to run. And again, we're going to have thread 1 run in its entirety. That is, it's going to go from start to finish. It's going to add its element. So thread 1 is going to create an element here. And it's going to set its value. Since it's not in the list, we're good to add it, and since the list is empty, because remember, thread 0 hasn't had a chance to update the element with the list. So now thread 1 is now going to set first and last both to point to the element that we just created. All right, that's great. And then we're going to increment the number of things in the list. So this is now 1. And then we're done. So context switch back to our other thread. Now, it believes that the list is empty. The list is not empty, but this thread isn't aware that the other thread has done something. It wasn't even aware that it stopped running. And so what thread 0 is going to do now is it, believing that the list is still empty, is going to set first and last to point to its element. And then it increments the counter. Uh-oh. What just happened? Well, let me tell you what just happened. We just made a memory leak. Because this element here that thread 1 added to the list now has no pointers pointing to it, which means that it's lost, which means you have a memory leak. And what can happen with list append is that the race condition can cause a huge memory leak. This was just 2 threads. What if you had a million threads trying to add an element to an empty list at the same time? It is entirely possible that 999,999 of those elements get lost. Race conditions can cause your output to be incorrect. They can cause memory or runtime errors, and they can also cause huge memory leaks. Race conditions are not fun. You do not want a race condition in your code. All right. So then, what are we going to do about it? Well, first off, when you're writing a piece of multi-threaded code, it's really important that you identify critical sections. You need to identify any of those shared pieces of memory, i.e. heap variables or global variables, where you could have multiple threads reading and writing at the same time. You need to identify this because that is where you will find your race conditions. And then you need to be able to, once you've identified those critical sections, you need to be able to fix them. That is, remove the race condition. But that's the question. How are we going to remove the race condition? Well, let's ask ourselves this question. Now, I know this term you're obviously not having this particular problem, but suppose you were on campus this term. Maybe let's go back to last term, or the last term you were on campus. And you're in DC and you need to use the washroom. Presumably, the bathroom stall you want to have to yourself. And that's actually what we want in a critical section. The only way to protect our shared variable, that critical section, is to let only one thread read or write that shared variable at a time. So we only want one thread in the critical section at a time, just like we probably only want one person in the bathroom stall at a time. Now, how are we going to prevent multiple people from entering the stall with you? Well, the bathroom stall has a door and the door has a lock. So when you show up to DC and you're going to the washroom and you see the stall and you're like, oh, the door is open. Nobody else is in there. So you walk in and you shut the door behind you. And then you can do whatever you want with your Dasani bottles or your laptops or whatever. All right. So then, what happens if you show up and the door is already locked? Well, you show up, you see the door is locked, and then you're going to say to yourself, I better wait. And so you wait for the door to open, and when the door is open, then you go inside and lock the door. And this is effectively what we need to do for critical sections as well. We need a locking door mechanism that we're going to have to check. Is the critical section available? If so, we enter the critical section and lock the door behind us. And if the critical section is not available, we need a way to wait until it is available. And then when we leave the critical section, of course, we're going to release them. There's a question on Twitch here, and hopefully I'll get to the answer to that in a minute. Let's just explore a little bit more about how this is going to work. All right, so let's, before we try to address this question here, let's actually talk about how would you implement a locking door mechanism for a critical section. Well, here's the easiest implementation of a lock you could possibly have. Let's have the lock be a Boolean variable. So here's my Boolean variable. Again, we'll come back to the volatile later. And we're going to assume that initially nobody owns the lock. That's a fair assumption to make because when you start a program, you want the door to be open. Because no thread has actually reached it yet. So we're going to set false to be open lock. Now what we're going to do is before I enter my critical section here, I'm going to try to acquire this lock. And when I try to leave the critical section, I'm going to try to release this lock here. So how do we implement acquire and release? Well, let's check this out. So let's implement the acquire as follows. So we are a thread and we want to get into the critical section. So we need to find out, is the critical section available? So we need to ask, is the value of the lock true or not? Because if the value of the lock is true, the critical section is locked and we can't get in. So if the value of the lock is true, we're going to spin. We're going to repeatedly sit there and knock on the door. Knock. Is it open? Is it open? Is it open yet? These are the annoying people, right? They just sit there and knock on the door. Hey, get out, get out, get out. That's what our lock acquire is going to do. When the lock finally changes to true, we'll break out of this loop and we will set the lock to true. And then we leave the lock acquire function and we enter the critical section. How do you release the lock? Well, that's fairly straightforward. You simply set the lock to false. Now, does this work? Well, we'd love it if it did work, but it doesn't work. Why does this not work? Here's the problem. Let's suppose, let's open up OneNote here and draw this out. It's kind of more fun to draw it out anyways, right? So, let's go to new page. Let's draw this out. So, DC is a funny bluey green building. Let's see, do I got it? Yeah, pink color. The DC-ish color. Here is our bathroom stall. And there, of course, is our toilet. And here is the door. And the door is open. Okay, so our lock starts out at false. All right. So, thread 0 and thread 1. Thread 0 enters. It checks. Lock is equal to false. So it doesn't loop. But before it can set the lock to true, context switch, and thread 1 runs. Now thread 1 sees, I guess I should put double equals here, the lock is equal to false. So it doesn't loop. And it sets lock to true. And now thread 1 is in the bathroom and the door is technically shut. But now we have a context switch back to thread 1 or thread 0. Let's suppose the context switch occurred because there was preemption. Totally possible to happen. Critical sections and these locks don't prevent context switches. Their goal is to prevent other threads from executing instructions in a critical section while another thread is in there. So they're going to force other threads to wait until the thread that owns the critical section has left. But in this particular case, what's going to happen now is we return, so there's a context switch, well, thread 1 owns the lock, and now thread 0 runs again, and it sets the lock to true, because it just continues where it left off. And now thread 0 is in the washroom. Oops. So this isn't what we wanted. And in fact, with this particular implementation of a lock, you could have 1 million people in the washroom at the same time. And that would be very, very awkward. So this implementation does not work at all. So we have a question about what happens if the context switch happens right as it finishes acquiring. So this is actually part of the problem that we're having with this particular section of code. What we have is in C, we think of these instructions as being very atomic in nature, and that is they are one line, they happen, and they can't be interrupted. But in reality, these operations, as you saw before, even assigning a variable a value is going to be at least 1 or 2 assembly instructions. And this here, testing whether the lock is equal to true, is actually many assembly instructions. What we have here is because this is not atomic, and this is called a test and set operation, we have the potential for a race condition here. So in this case, we have a race condition. This does not work. How we solve the problem is we need some kind of atomic test and set operation. How do we get an atomic test and set operation? Can we do it with just C? Well, this is kind of complicated. So the answer is, technically speaking, you could implement true locks using only C code. There's many algorithms to do this. There's Dijkstra's algorithm, there's Peterson's algorithm. However, these are not general purpose, efficient implementations of a lock. You have to understand that we need locks to be really, really quick. We don't want them to be slow because these are going to be a core part of the kernel of the operating system. They're going to be a part of many multi-threaded programs. We want the implementation of the locks to actually be as simple as possible. And Dijkstra's algorithm and Peterson's algorithm, they have a lot of limitations and they're just not that efficient. So while they technically do work, they don't work for an operating system. So what are we going to do then in the absence of a way of doing this in C? And the answer is we're going to rely on hardware. So specifically, we are actually going to rely on atomic test and set operations provided to us by the architecture itself. So for example here, x86 or x64, that's the Intel architecture, that offers an atomic instruction known as exchange. It's effectively an atomic swap. What atomic means is that the operation completes without being interrupted. Now the pseudocode for exchange is actually quite many. It looks like it's many instructions, but it cannot be interrupted. And what happens is you pass exchange a value and an address, and it's going to record the old value at the address. It's going to then put a new value at the address and return the old one to you. So if you wanted to use exchange to give you an atomic test and set, we want to set the lock to true. So we would exchange true for the value of the lock. And then if the lock is true, we exchanged true for true and it does nothing. The lock is still not available. And if the lock is false and we're trying to take the lock, then exchanging false for true, we end up owning the lock. So to look at the implementation of our lock acquire using exchange, it's now the following. So while exchange returns true, that is while the lock, we're swapping true for true, keep looping. The lock isn't available. Only when exchange returns false, which is the old value of the lock, do you actually own the lock and stop looping. Now, you might be tempted to believe that this is how we call assembly code in C. This is not how we call assembly code in C. I wish it was. It's not. I'll show you it later. We, by the way, have no expectations that you know how to use assembly inside of C in this course. Now, this particular kind of lock that we have implemented, by the way, is called a spin lock. And it's called a spin lock because it has a busy wait. It is actively spinning, repeatedly knocking on the door, asking, are you done yet? Are you done yet? Can I have the lock? Can I have the lock? It's spinning. This kind of lock is an unfortunate necessity, and it's already implemented, by the way, by OS 161. But what we're asking you to do in assignment 1 is to implement a lock, not a spin lock, a lock. And a lock is different from a spin lock because it doesn't spin. And we'll talk more about that next week. Now, that's x86 implementation. Normally here, we would actually show you Spark's compare and swap instruction, but nobody knows what a Spark is anymore. So I decided, let's talk about ARM. So many of you have seen ARM. ARM is a RISC architecture just like MIPS. By the way, x86 is not RISC. And what ARM has is more of a barrier. So instead of a single atomic operation, it actually has a pair. Excuse me. The pair is LDREX and STOREX for load exclusive and store exclusive. They act as a barrier and they have to be used together. And what's going to be happening is the load exclusive operation is going to look at the value that is stored in the lock. And then it's going to call the store exclusive operation. And if the value in the variable has not changed between the load and the store exclusive operations, and they should be next to each other in the code, but if it hasn't changed, the value hasn't changed between those two, it means no other threads were writing to that variable, and therefore it is safe for you to write the variable. All right. Now, how do you use this? Well, how you're going to use this is as follows. So we're going to need to make a helper function. I hate using that word. We're going to write a function called arm test and set. And what it's going to do is it's going to check whether or not we successfully were able to store a new value in our lock. And if we were able to store a new value in our lock, then we're going to return the old value of the lock, and otherwise we're going to return true. So very quickly here, we get the old value at the lock, or the current value at the lock, stored in temp, and then we're going to try to store a new value at the lock. If the value of the lock hasn't changed between this line and this line, then the store exclusive succeeds, regardless of whether we are changing the lock from false to true or true to true. Store exclusive isn't aware of locks. It's just simply saying, has the value of this variable changed since the load exclusive? And if not, we successfully do it. Otherwise, it returns a failure. So if the store exclusive succeeded, instead of returning false, which is the old value of the lock, you'll notice return the old value of the lock. And the reason here is because the store exclusive will succeed if we are swapping true for true. So we have to return this temp value here. And then, of course, if the store exclusive failed, it means that in between the load and the store, the value of the thing changed, which means we weren't able to swap the value, so we failed. We return true. And the reason why we want to return true in this case is we want to spin so long as arm test and set doesn't return false, because false would indicate that we were able to set the value of the lock. All right, so that in a nutshell is how ARM does it. Now you're probably sitting back and wondering, well, how does MIPS do it? Oh, the same way, except different instructions. So with MIPS, we're also using this barrier, and what the barrier does is you have load linked, which gets the current value of the variable, and store conditional, or SC. And if store conditional is going to succeed and store the new value at the address, if in between the load linked and the store conditional, the value of the variable doesn't change. And store conditional will fail if the value of the variable has changed between LL and SC. So that's it. Now, if we look at how we implement then this acquire in MIPS, it looks the same as we did with ARM. And you end up with a MIPS test and set function where we just replace load rex and store x with LL and SC, but it behaves the same. All right. Now, at the bottom of this page, I actually have given you a little bit of a truth table-like thing. And what this is showing you is if the initial lock value is false, and at the time we execute load linked, it was false, and at the time we execute store conditional, it is false, then after we execute store conditional, the new value of the lock is true, store conditional succeeded, and therefore we own the lock. So this is telling you all of the different cases for under which situations will we own the lock and under which situations will we not own the lock. And you'll notice there are 4 different situations here. Now, this is a rather complicated idea, so we will review it again next class. I just want you to mull on what's going on here. So, then, trying to find my mouse here. I usually have X eyes, but I don't have it open today. I'm going to leave it here for today. In our next episode, we'll review how MIPS load link and store conditional implement a spin lock. And then we're going to introduce locks, not spin locks, locks that block, which will be useful on your assignment 1. And then we'll get to start talking about semaphores and condition variables, which are also going to be very useful for you on assignment 1. Now, if I'm going to give you a little extra time to respond to that question post on Piazza about if you could ask one of the original Unix developers anything you wanted, what would you ask them? You're probably sitting there wondering, why do I keep bothering you about this? I might have something up my sleeves, a little surprise for you, if you will. You will find out in the coming days, shall we say. All right then, so I hope you all have a wonderful weekend, and you're welcome to read ahead to get started on assignment 1. Don't forget to start doing the quizzes on Learn. You can, of course, you can save them all till the end if you want, or you can do them as you go. It's really your choice, but they are posted. So we will see you on Tuesday of next week.